Hey, what's up? It's Miss Wesley. It's time for some calc yet again, so you can tune in on page 10 of the volume packet to start with these examples. And you'll notice at the top it says today we're going to continue revolving regions around lines called the axis of revolution. But this time we're not going to pick a line that's the x-axis or the y-axis. It might be some other line like the line y equals 1. Here's a prop that I wish I had in my last segment, so I want to show it to you now. Let's say I take this region, it's in 2D here. This is actually a party decoration that I was talking about before, and I want to spin it around the x-axis. Well, when the shape gets revolved, it opens up and you get this 3D figure. So we've seen some shapes, and we've tried to graph them the best we can. We've seen some shapes so far that have looked like maybe like a sphere or like a Christmas tree ornament, and others that look more like the inside of a flashlight or a bowl, and we'll see another one here. Let's get into it. It says find the volume. We have a couple sketches here. Find the volume of the solid formed by revolving the region bounded by the graphs of, let's see, an upside down parabola, f of x equals 2 minus x squared. So that's this graph here. That's your top function. I should probably label that top function. And the line g of x equals 1 or y equals 1 is going to be the function that bounds the region from the bottom. We've seen this a little bit before with area between curves. I want to see where it comes into play with volume. So here's your shaded region. We want to, can you picture this? We want to put this in motion and spin it around the line, not an axis, not a coordinate axis, y equals 1. So this line here is our axis of revolution. And here's a rough sketch of the, kind of looks like an eyeball, the 3D version. You're going to get, if this is a little rectangular shape here that got spun, it's going to spin into a circular disc. You get a typical disc here, where we've seen in the other problems we've tried, the radii have changed. The radius value has changed throughout the shape, but we can use area of a circle to get the area of a typical disc. One more little depiction of how this is going to look. So here's your shape. You've got top function, bottom function, and the region in between. We want to revolve this around the line y equals 1. So here's the shape being formed, and I'll spin it around in a second too. We want to see if we can integrate and use calculus to get the volume of this shape. Okay, let the fun begin. Let's go back to it. Off to the side, let's find the area of a typical disc. And I'll just draw out a disc here. So I have a disc that's shaped like a circle. The other day we were calling the width of the disc, that little delta x. You don't really see much of it, but it's as if you're stacking a bunch of those shapes to make up the entire volume of the figure. And right through it, you have this axis of symmetry, x equals 1. And we want to look maybe at this 2D picture and see if we can write an expression for the area of this typical disc. It's going to start with the radius value. Let's look at the picture and see if we can get some help with that. The radius of each disc is going to be this blue height that I'm drawing in here. It's always going to be the entire height up from the x-axis up to the top of the shape, but you're subtracting this chunk of dead space in the middle there. So you just want the difference between the top function and the bottom function. So use the top minus bottom principle. The function bounding the region from the top in terms of x is 2 minus x squared. The function bounding the region from the bottom is just the straight horizontal line, y equals 1. So you'll have top, I'll write t for top, minus b for bottom, like that. And that can be simplified. The radius is going to equal, in terms of x, negative x squared plus 2 minus 1, so plus 1. Okay, can you plug that into area equals pi r squared? That's the next step. So we'll call it pi, and then this radius, negative x squared, top function minus bottom function, plus 1, squared for a pi r squared. Okay, I think we are good to go. This is going to take a little bit more simplifying. Let's go volume. We are integrating, right, from one x value to another. This is a horizontal axis of symmetry, so it's very important to remember we're doing this entire question in terms of x and not y. So from what x value to what x value? It looks like this low one to this high one, negative 1 to 1. What are we integrating? We're integrating area. That's what the formula for volume would be. So we'll go pi, and then this binomial squared. And we want to think of the most convenient way to get an expression for this antiderivative. One thing that's always convenient is sliding the constant outside of the integral sign. The pi can be separate. Another thing that's convenient, I'd rather just quickly FOIL this with itself so that I can just see each term one at a time. So to square a binomial, we square the first term, so you get x to the fourth, plus double the product, minus 2x squared, and then the last term is going to be a plus 1. You square the last term. And I think we're ready to integrate. Pi, you've got x to the 5th over 5, minus 2/3 x to the 3rd, plus 1x. Evaluate it from -1 to 1. Feel free to pause the video while you type the numbers in. Here's the plug-in. Pi, let's plug in 1 first. So 1/5 minus 2/3 times 1 plus 1. Subtracting the same values with -1 plugged in. So -1/5 minus 2/3 times -1. So let me put plus 2/3 on the inside of parentheses and minus 1. All said and done, feel free to pause. Exact value is going to be 16/5 pi, or 16 pi over 5. Units cubed because we've just calculated volume, and decimal approximation, which is totally fine too, about a 3.351. Okay, so not too bad, but good to have this example down. First time ever, our axis of revolution is a line other than the y or the x-axis, and this is a good example where everything's done in terms of x. Your axis of revolution is a horizontal line. Here's when things switch. Let's look down at number 2. In this one, I have to think a little bit differently. While graphing the region won't be so bad, it's going to be as easy, especially in 2D, it'll be as easy as graphing some lines. I'm not too worried about that. But look, you're revolving the region bounded by these 4 graphs about a line that is vertical. The line x equals 5. 1, 2, 3, 4, 5 would be here in this second picture. So just something to watch out for when your axis of revolution is going to be vertical. We're thinking in this one in terms of y's and not x's. I'll just say use y's. And we'll see where this comes into play in a second. Again, don't let drawing the picture stress you out. A lot of these problems, you're provided the picture, and this one we're just going to try to sketch it for ourselves, and I'll show you a little demo of it too. So first we need to graph the line y equals x. Not my forte on this program, but I will try my best. Y equals x is diagonal, goes right through the origin. Okay, so that tool really helped. Then I need, so that was the first line. Y equals 0, I don't have to really worry about because that is, x-axis and y-axis are already drawn for us. So now I have to make sure that I'm good with sketching y equals 4 and x equals 5. So y equals 4, maybe I'll do the same thing with the line tool. And y equals 4 is up here. And x equals 5 is over here. We've just made ourselves a trapezoid. So I'll have x equals 5 come down like that. Okay, and y equals 0 was beneath it. I want to shade in the region in question. Let's shade in red here. This is the region that we're going to revolve. Okay, so this trapezoid. We're going to spin it around a vertical axis of revolution. So it's important to know which y values you're between. We want to do this whole thing in terms of y's. And we want to see if we can easily draw this in 3D. So here's my advice. I'd say first, sketch your 2D version on this picture. So sketch the line y equals x here. And then maybe you can connect it, or you don't have to connect it like that. Can you mirror it over the axis of revolution? So since you're spinning it around this line, can you mirror it to this side? So I'll just draw the same thing coming down, and it's going to go over to 10. This is x equals 5. This was 0. I'm going to go all the way to 10 if you're thinking of a scale here. And then to make this look a lot less like a big plateau, look a little bit more 3D, instead of connecting it with those lines across the top and bottom, I might actually just delete those little segments. And what I'll do is I'll draw the top and bottom connected with circles. I'll draw a circle around the top and maybe part of a circle around the bottom. You're supposed to get some sort of a megaphone type of shape if the megaphone was sitting on the ground facing down. A disc would actually be kind of oriented the other way in this picture. So if you had a rectangle coming out from there and it spun around that axis of revolution, you would get a circular disc shape like that. With a radius, I'll draw the radius here coming out, and I'll just label it R. My picture, not the best. This might help. Take a look at this graphic. So you've got the line here. I want to revolve it around the vertical line, axis of revolution, x equals 5. This is a way better depiction of that 3D shape. And again, I always mention that it looks like it's hollow, but it's going to be filled in. The volume we calculate will be for that filled in shape. Okay, so let's take a look. We would want to see across cross-section and come up with a good expression for the radius of that cross-section. So your disk is going to be something like this. And then last time for the radius, we used top function minus bottom function. Same idea here, but I want to use right function minus left function. Your radius coming out from that center line, and that's what's always a little bit harder to picture here. The radius down here is going to be all the way 5 units. At the top, it's as short as 1 unit. And everywhere in between, you can always calculate that radius value by taking the right function, the number 5, minus the left function. This minus that should give you, like this whole distance minus this little chunk here should give you the radius you have left. So I'll write that here. I'll say r equals the right function, which is x equals, we said 5, and we'll use a 5 there, minus the left function, so this is y equals x. And I'm going to use what x equals in both cases. So x equals the number 5 for the right function. It equals the expression y for the left function. So 5 bounds the region from the right. And x equals y bounds the region from the left. Notice I could have put 5 minus x here, but I'm thinking about this vertical axis of revolution and that advice that we need to do everything in terms of y's. I don't want to have 5 minus x here. I want to have 5 minus what x equals in terms of y. So 5 minus y should do the trick. This will give you an expression for area, and we always use the pi r squared, the circular area. So pi times the radius, 5 minus y squared. We'll take this back to an integral. Where are we integrating? Let's get our limits of integration. So volume equals, from what y value to what y value? I know the x's go 0 to 10. The y's are what we care about. The y's go 0 up to 4. So we'll put those two values there. And we'll integrate this area expression that we just found. So pi times 5 minus y squared dy. Okay, very similar to the last one in terms of calculating it. Move the pi outside. Carefully expand the binomial so you have an easier time integrating this thing. So we'll go 5 squared, so 25, minus double the product, minus 10y, and then plus y squared, squaring the last one. And we will carefully take an antiderivative. So 25, tag on the variable, 25y, minus 10y squared over 2. So 10 over 2 just gives you 5y squared, plus y to the third over 3. Evaluated from a low to a high y value. Plug in 4 first. So I'll show the plug-in. Feel free to let the calculator take it from here. 25 times 4 is 100, minus 5 times 4 squared, so 5 times 16 is 80 there, plus 4 cubed over 3, 64 thirds. And here's a case where we get lucky. Minus 0, minus 0, minus 0. 0 is not going to affect this too much. I would type all this in, hit math frac, put a pi with it for exact value. So 124 pi over 3 is going to be your exact amount of cubic units of area. Decimal approximation, I did nearest thousandth, 129.852. So we're just scratching the surface here, and we've got 2 examples under our belt. One, the first one where the axis of revolution was horizontal, and we used x's in the entire problem. And here an example where the axis of revolution was vertical, and so we needed to use y's. What I think is trickier about these questions in general is this whole finding the radius thing, and it's usually going to be one function minus another. You can trust that if you are have a horizontal axis of revolution, you can use top function minus bottom function to find that radius. And it would be right minus left if you're oriented the other way. I just wanted to take a peek at the practice examples on the next page and get you set up for number 3 in terms of the picture. When you do number 3 on page 11, it's not bad to draw y equals square root of x. I have those 3 classic points I always put on there, 0, 0, 1, 1, and 4, 2. But be careful. You're not spinning it around the axis like x equals 4. This is a vertical axis, x equals 3. So what that tells me is this whole problem is in terms of y's and not x's, and I wanted to help you with those limits of integration. You're integrating, if this is your region in question, and you're going to spin it around this line, you're going to get this like 3D, this is a really rough sketch, but maybe like an upside down cereal bowl, like that, with a circular disc in the middle. The y values here, it goes from 0 up to every y is the square root of x. So you're integrating from 0 to the square root of 3. Your integral eventually is going to have those y's as its limit. Stay tuned. We'll get more into this in the coming days. See you later.